Okay, so we're going to start Unit 9 today. And Unit 9 is all about energy. And we've already talked about some energies already, but we have to tie in some more thermochemistry. And that's what we're going to do today, or start to do today. And we're going to talk about a concept called entropy. And entropy, we're going to use the letter S to designate entropy. And we'll use the deltas, change in entropy. So that's definitely nothing new. The delta, that little postscript 0 means at standard conditions, and we're going to assume standard conditions unless told to us otherwise. And then again, S is going to be this new concept called entropy. So we have to find out what entropy means. But we will be using this same equation that we used with delta H, change in enthalpy, and it has us go to a table and find some standard, in this case, entropies. Last time it was enthalpy, and add up all the product numbers, add up all the reactant numbers, and subtract those from each other. And then coefficients will also play a part in that balanced chemical equation. Okay, so maybe we should try to get a definition of this first. And we're going to come back to here. But entropy is the measure of how spread out or dispersed the energy of a system is. Basically, for us, we can kind of think of it as a measure of disorder. The more disorderly something gets, the more entropy that particular thing has. This is the true definition, but in our practical, in our lab or the kind of questions we're going to get in class, it might be easier to kind of think of it as the randomness or disorder of a system, okay? Because typically we're going to be talking about the system. So we'll come back to that slide in a second. So we're going to talk in terms of something called thermodynamically favored. That means, does it happen on its own? Reactions that are we used to call, in AP chemistry, we used to use the term spontaneous, meaning that it happens without outside interference, but now we'll call it thermodynamically favored. So do any of these things happen on their own? Will lumps of sugar dissolve in hot coffee? I think yes, that would happen. Will water boil at 1 atmosphere and 65 degrees Celsius? That's a no. That is not thermodynamically favored. Will toilet bowl cleaner act upon lime deposits? Not that you guys are doing a lot of toilet bowl cleaning, but that reaction will occur without any outside influences. Melting of an ice cube at room temperature? Correct, that will happen. Heat flowing from colder to hotter? No. Iron exposed to water and oxygen to form rust? Yes. So there are things that we can observe that happen on their own. There are some things, by the way, that will happen on their own, but you need to overcome the activation energy of them. Those are still thermodynamically favored, okay? But there's other things that, even if you overcome the activation energy, they're not going to happen and continue to happen, like the ones I've exited off here. So we've already got the definition of entropy. And the reason we're going to talk about entropy is because all reactions have two driving forces. When I say all reactions, all thermodynamically favorable reactions, or in this case processes, because they don't all have to be reactions, they could be physical processes, are either about enthalpy, going towards a lower energy state, or increasing in disorder, okay? And then you can also call that randomness, okay? And this relates to the second law of thermodynamics. We had our first law many units ago that said that you can't create nor destroy energy. And the second law says that the universe is always increasing in entropy, or in disorder, or in randomness. And an example of this would be, and I've heard a couple other people mention things like this. If you would, for instance, not do anything to your room over a period of time, let's say, so where you could really observe it, let's say 10 years. Over 10 years, if you didn't clean your room, I think you would find it to be more disorderly than the last time you cleaned your room 10 years ago. So I don't think we're going to get to use this equation, but the system and surroundings are related to each other, for sure. But this is where we're going to be interested in. This first item was in your textbook, so I wrote it down. But delta S of the system, if it's greater than 0, it's increasing in disorder. If it's less than 0, it's decreasing in disorder. And then gases, because they are so far apart from each other and they're moving so fast, have tremendous entropy compared to solids or liquids. So if we have to look at some reactions and there happens to be some gases, some liquids, and some solids in the reaction, we're going to be only considering the gases in terms of entropy. Yes, liquids have a little more entropy than solids because they're free-flowing, but they're still highly structured. Oops. So can we make some predictions here? We have a liquid going to a solid. So delta S would be less than 0. It's going to become more orderly, less disorderly. Cooling. If you cool a gas down, it will not be moving as fast. It will have less disorder. We have 1 gas plus 3 gases, making 2 gases. So 4 gases going to 2 gases. This is also less than 0. Okay. A solid, or 2 solids, going to 2 solids and 3 gases. So ultimately for us, 0 gases going to 3 gases. That is going to increase in disorder. If you would dissolve sugar into water, that's solid going to aqueous. That's going to become more disorderly. We can quantify these later. We're not going to do that right this second here. And the way we're going to quantify that is the same exact method that we used with delta H's earlier in the year. We're going to use it with delta S's. You go to the same area of the textbook, just a different column. So we had a delta H column. Now we go to the entropy column. And if you go find these values, again, be very careful to find CO2 gas, not CO2 solid. Make sure you find the right states of matter. But it's the same work. I'll do the first one completely for you. So I went in the back of the book, I found calcium oxide, and it had a value of 213.6. And there's one of all of these, so we have to multiply it by 1. And then we have a carbon dioxide at 39.8. I have to double check that. Let me double check those numbers. I'm not feeling those numbers right now. We have carbon dioxide. Yeah, I was thinking that the carbon dioxide was the 213.6, sorry. So those are right. I just had them in the wrong order. Okay, so this is the CO2's number, and this is the calcium oxide. Why did I know that was the case? Because carbon dioxide's a gas. It should have a lot more entropy than calcium oxide. Okay, so then let's go back to finishing this. We need the calcium carbonate number, and that is 92.9. Excuse me. So when we do that math, we get a delta S, by the way, standard, of 160.5, and the units that went with that in the book that go with entropy are these. Let me rewrite that again. 160.5. Okay. So the second one, I got 2 ammonias, and then the reactants, I had 191.5 for nitrogen and 3 times 131 for hydrogen. Put those together, and I got negative 198.5 joules per Kelvin mole. Now let's see if we can double check these. The first one, we had 0 gases going to 1 gas, so that should be a delta S greater than 0, and 160.5 is greater than 0. So we can't verify perfectly if the answer is right, but we know if we're really wrong. And then the second one, we have 4 gases going to 2 gases. So that should be a delta S that is less than 0, and negative 198.5 is certainly less than 0. So I feel a little bit better about those 2 answers. Again, in your textbook, we're not going to do any plug and chug with those, but you could. So if you have a delta S and you have a temperature, you could get the delta H. Or if you have a delta H and a temperature, you could get the delta S. This wouldn't be any more than a plug and chug type of question. So I don't think this is going to be one I would want to spend very much time looking at. And then this third law of thermodynamics, it's a good time to throw this in here, but I've never seen this on a test question on the AP test in May. This will either be no questions on my test or 1 question on my test, but I thought we should handle this anyhow. Third law of thermodynamics states that if you have a perfect crystal would have to be something with no imperfections, just one particular atom of an element repeating, some kind of lattice probably. And if it's at 0 Kelvin and it's a perfect crystal, it has no entropy, no disorder. Okay? I wouldn't say you'd have to really worry about that either. That goes with that third law. These are the kind of typical questions you would get that deal with this section here. So again, we already have these answers. Whoops. We already have these answers, but let's figure out why. The greatest increase in entropy. So we need something that has the least gases to the most gases. And this goes from no gases to 1 gas. Okay. And then which one has a delta S positive, greater than 0? It's the same exact idea. Least gases to most gases, and it's almost the same sort of setup there. We have no gases going to 1 gas. And that will conclude our introduction to entropy.